All right. This is going to be a good one. All right. So first, we're going to talk about a Ferris wheel. So, looking for a thrill? Then consider a ride on the Iron Dubai, the world's tallest Ferris wheel. Located in Dubai, the most populous city and the financial and tourism hub of the United Arab Emirates, right? The wheel soars to 820 feet, about 1.5 tenth of a mile. Described as an observation wheel, riders enjoy spectacular views of the Burj Khalifa, the world's tallest building, and the Palm Jurayim, a human-made archipelago, excuse me, home to over 10,000 people and 20 resorts. Awesome. As they travel from the ground to the peak and down again in a repeating pattern. In this section, we will examine the type of revolving motion around the circle. To do so, we need to define the type of circle first, and then place the circle on a coordinate system, right? Then we can discuss the circular motion in terms of the coordinate pairs. All right. So from that, I gather that you might understand what we're getting into. So here's our first topic. We're going to be finding functions for sine and cosine. To define our trigonometric functions, we begin by drawing a unit circle. So this is a circle centered at the origin with radius 1, right? As I'm going to show you. The angle in radians that T intercepts form an arc of length S, right? I remember our arc length formula is S is equal to RT. And knowing that R is equal to 1, we see that the unit circle is S equal to T. All right. Good stuff. Good stuff. So recall that the X and Y axis divide the coordinate plane into four quarters called quadrants, right? We label these quadrants to mimic the direction of a positive angle, or the direction a positive angle would sweep, excuse me. The four quadrants are labeled 1, 2, 3, and 4 in Roman numerals, right? So, like with the I kind of looking thing for one, etc., right? So for any angle T, we can label the intersection of the terminal side and the unit circle as by its coordinate xy. So the coordinates x and y will be the outputs of the trigonometric function. So f of t is equal to cosine t, and f of t is equal to sine t, respectively. This means that x equals cosine t and y equals sine t. All right. And here's our figure to illustrate that. This is the unit circle where the center angle is t radians. All right. This is the center angle right here, t radians. Let's talk about the unit circle. So a unit circle has center at 0, 0 and radius 1. In a unit circle, the length of the intercepted arc is equal to the radian measure of the central angle t. All right. Let x, y be the endpoints on the unit circle of an arc of length s. The x, y coordinates of this point can be described as functions of the angle. So defining sine and cosine. Now, that we have our unit circle labeled, we can learn how the XY coordinates relate to the arc length and the angle. So the sine function relates a real number t to the y coordinates of the point where the corresponding angle intercepts the unit circle. More precisely, the sine of an angle t equals the y value of the endpoint of the unit circle, right? And of an arc of length t, right? As seen in figure 2. The sine is equal to y. Like all functions, the sine function has an input and an output. It is important to measure, right? Excuse me, its input is the measure of the angle. Its output, right, is the y coordinate of the corresponding point on the unit circle. The cosine function of an angle, t, equals the x value of the endpoint on the unit circle of an arc length t, right, which you can see in figure 3, and the cosine is equal to x. So here we go. This is figure 3. Right? Notice that we have x, y. X is for cosine, y is for sine. That's the secret. So because it is understood that sine and cosine are functions, we do not always need to write them with parentheses. Sine t is the same as sine of t with the parentheses, right? And cosine t is the same as cosine of t with the parentheses. Likewise, cosine squared t is a commonly used shared notation for cosine of t squared. Be aware that many calculators and computers do not recognize the shorthand notation, right? When in doubt, use extra parentheses when entering calculations into a calculator or computer. All right, sine and cosine functions. If t is a real number and a point xy on the unit circle corresponding to the angle t, then cosine of t, or cosine t, excuse me, is equal to x, and sine of t is equal to y. We got a little how-to. So given a point P, XY, right, on a unit circle, corresponding to an angle of t, find the sine and cosine. That's how you do it. Step 1, the sine of t is equal to the y coordinate of the point P, right? Step 2, the cosine of t is equal to the x coordinate of the point P. That's it. Nice and simple. You guys try for a little bit. as you can see here. It's good. So given this, right, what I want to know, what is cosine and what is sine? So you can very simply just say cosine t equals, give me a number. Don't overthink it. Just the x coordinate. Thanks, man. Appreciate it. What's the x coordinate here? What's the x coordinate? Yeah, that's it. So what is sine of t? Don't overthink it. It's just the y coordinate. Don't overthink it. It's just the y. What's the y here? The y coordinate. Radical 3 over 2. That's it. Full credit. Questions on that? It be like that sometimes. I mean, not on the test, but it's like that on your homework. Just type in the answer that you see. No? Appreciate it. So finding sines and cosines of angles on an axis. The four quadrantal angles, the corresponding point on the unit circle falls on the x or y axis. In this case, we can easily calculate cosine and sine from the values of x and y. Appreciate it. Thank you. So it says calculating sine and cosine along an axis, right? We want to know what is cosine of 90 and what is sine of 90. Very simply, right? This is my x, this is my y, right? We know that this is 0 degrees, this is 90 degrees, this is 180, this is 270, right? And I'm telling you that it's at 90. So there would be a point here on the unit circle, right? And this point would be what? Right? This point would be 0, comma 1, right? So now when I say what is cosine of 90 degrees, right? I'm asking you literally what's the x coordinate of this point here? So it's 0. What is sine of 90? Right? And then that's going to be the y coordinate 1. Questions on it? Yeah. And if it's not there, assume radian. That's the point on the unit circle, right? For 90 degrees. Remember, 90 degrees is on the top. Yes, it is. Hmm? That's it. That's all I'm asking you about. The x coordinate is cosine 90 and the y coordinate is sine 90. All I want is 0 and 1. Yeah. 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 And there's two of them. There's yeah. Oh, I'm sorry? That's for graphing and exponential, you need 3 points. Is the sine and cosine. Yeah. But all I'm asking about is 1 point, given one angle. Didn't get to tangent yet. Yeah. So the Pythagorean theorem, right, excuse me, the Pythagorean identity, excuse me. Now that we can define sine and cosine, we will learn how they relate to each other and the unit circle. Recall the equation of the unit circle is equal to x squared plus y squared is equal to 1. Because x equals cosine t and y equals sine t, we can substitute for x and y to get cosine squared t plus sine squared t is equal to 1. This equation, cosine squared t plus sine squared t equals 1, is known as a Pythagorean identity, right? And here we go, we got it right here, right? So 1 is equal to x squared plus y squared, which is also equal to cosine squared plus sine squared, right? Then we can use the Pythagorean identity to find the cosine of an angle if we know the sine or vice versa, right? However, because the education yields two solutions, we need additional knowledge of an angle to choose the solution with the correct sign, right? If we know the quadrant, that's what I'm trying to say, where the angle is, we can easily choose the correct solution. All right. This one's important. So the Pythagorean identity states that for any real number t, cosine squared t plus sine squared t equals 1. All right, so the how to, so given the sine of some angle t and its quadrant location, find the cosine of t. Here's how you do it. Step 1, substitute the known value of sine of t into the Pythagorean identity. Step 2, solve for cosine of t. Step 3, choose a solution with the appropriate sign for the next values in the quadrant where t is located. So finding a cosine from a sine or a sine from a cosine. If sine of t is equal to 3 over 7 and t is in the second quadrant, find cosine of t. All right, let's take a look. So t is in the second quadrant, right? So here we go. There's some point here, right? And this is t in the second quadrant, right? Sine is what? Opposite over hypotenuse. So this would be what, 3 over 7, right? Now, I want to find what this x value is right here, right? To do so, we could very simply just use the Pythagorean theorem. A squared plus b squared equals c squared. Plug in the numbers, and that's it. So let's say that I have 3 squared plus b squared equals, wait, hold on, what am I doing? Hold on. Sorry about that. I would have 3 squared plus b squared equals 7 squared. 9 plus b squared equals 49. Subtract 9. So I have b squared is equal to 40. Then you want to square root both sides. All right, so b is equal to whatever the square root of 40 is. In our case, that b is actually x. Questions on this? Hmm? 6.32? Okay. Whatever it is. Yeah. I could simplify this down further, make this square root 10 times square root of 4, and then said, what is this? This is like 2 times 2 square root 5, something like that. So 4 square root 5, you could say as well.
Whatever information they give you to find everything else.
Pretty much. Pretty much. All right. That's possible. They could ask you that. Yeah. So if they're asking you for the coordinates, they're literally just asking you solve for x, solve for y, x equals this group, y equals this group for the answer, and that's it. One second. All right, let's talk about finding sine and cosine of special angles. This is the real good stuff right here. All right. So we've already learned some properties of special angles, such as the conversion from radians to degrees, right? We can also calculate sines and cosines of the special angles using the Pythagorean identity and our knowledge of triangles, right? Finding sines and cosines of 45-degree angles. So first we will look at an angle of 45 degrees or pi over 4, as shown in the figure right here, right? So a 45, 45, 90 triangle is an isosceles triangle, right? So that the x and y coordinates of the corresponding point on the circle are the same. Because the x and y values are the same, the sine and cosine values will also be equal. All right. So basically, x and y here are the same. All right. So at t equals pi over 4, which is 45 degrees, right? The radius of the unit circle bisects the first quadrant angle. This means the radius lies along the line y equals x. A unit circle has a radius equal to 1. So the right triangle formed below the line y equals x has sides x and y, where y is equal to x, and a radius equal to 1. So there you go. So real quick, from the Pythagorean theorem, we get that x squared plus y squared is equal to 1. Substituting y equals x, and we get x squared plus x squared is equal to 1. That's gonna, when we add them together, the coefficients become 2. So we have 2, or combined like terms, excuse me, we have 2x squared. All right. So we have 2x squared is equal to 1. Then we want to just solve for x very simply, right? So divide by 2, square root both sides, blah, blah, blah. So we get plus or minus 1 over the square root of 2, right? And then in quadrant 1, x is equal to 1 over the square root of 2. That's it. So in quadrant 1, x equals 1 over square root 2. At t is equal to pi over 4, or 90 degrees, right? So x comma y is equal to xx, which is equal to 1 over the square root of 2, right? X and y. So cosine of t is equal to 1 over the square root of 2, and sine of t is equal to 1 over the square root of 2, right? If we rationalize the denominators, right, what do we get? So we're going to get cosine of t is equal to square root of 2 over 2, and sine of t is equal to square root of 2 over 2. Therefore, the x-coordinates of a point, right, on a circle of radius 1 and an angle of 45 degrees are what? Radical 2 over 2, comma, radical 2 over 2. So finding sine and cosine of 30 degrees and 60-degree angles. Next, we will find the cosine and sine of an angle of 30 degrees, or pi over 6, right? First, we will draw a triangle inside a circle with one side of the angle at an angle of 30 degrees, right? And another at an angle of negative 30 degrees, right? As shown in the figure. If the resulting two right triangles are combined into one large triangle, notice that all three angles is of this larger triangle will be 60. Right? So we're talking about this figure right here. Look at figure 12. Boom. This is our special right triangle. Because all the angles are equal, the sides are also equal. The vertical line has length 2y, and since the sides are all equal, we can also conclude that r is equal to 2 over y, right? Y equals 1/2 r since the sine of t is equal to y. So sine of pi over 6 is 1/2 r. Sine pi over 6 is equal to 1/2 times 1 times 1/2. All right. Using the Pythagorean identity, we can find the cosine value easily. So cosine squared of pi over 6 plus sine squared of pi over 6 equals 1. Right. Then we have cosine squared of pi over 6 plus sine of, excuse me, plus cosine of 1/2 squared. Combining them together, right? Cosine squared of pi over 6 is equal to 3 over 4. That's it. So use the square root property. Since y is positive, choose the positive root, right? Okay. All right. The XY coordinates for the points on the circle of radius 1 and angle 30 degrees are radical 3 over 2 and 1 over 2. At t equal to 1/3 60 degrees, the radius of the unit circle 1 serves as a hy hypotenuse of the 30, 60, 90 degree right triangle. Bad, as shown in figure 13, right? Angle A has measured 60 degrees. At B, we draw the angle ABC and measure of ABC. And last one, we know that, excuse me, we know the angles in triangle sum of one up to 180. So the measure of angle C in is also 60 degrees. Now we have a equal li liberal to, excuse me. Now we have an equilateral triangle because each side of the equilateral triangle ABC is the same length, and we know that one side of the radius of the unit circle, all sides must have length 1, right? For a unit circle. There you go. So the measure of angle ABD is 30 degrees. So if double angle ABC is 60 degrees, right? Line BD is a perpendicular bisector of AC, so it cuts AC in half. This means that AD is 1/2 the radius, or 1/2. Notice that AD is the x coordinate of point B, which is the intersection of the 60-degree angle and the unit circle. This gives us a triangle bad with hypotenuse 1 and x is of length 1/2. So from the Pythagorean theorem, we get x squared plus y squared equals 1. We're going to substitute x equals 1/2 into this, right? Then you just solve for y, right? So 1/4, we're going to multiply that, like that. So since pi/3 has a terminal side in quadrant 1 where the relative positive, we'll choose y equals square root 3/2, the positive value. Right? So at t equals pi/3 or 60 degrees, the xy coordinates for the point on the circle of radius 1, right, at an angle of 60 degrees are 1/2 and square root 3/2. So we can find a solution. So we can find the sine and the cosine. Remember, they gave me the x and the y here. So x comma y is equal to 1/2 square root 3/2. And we have x is equal to 1/2, y is equal to radical 3/2. And then cotan, yeah, is equal to 1/2, right? And sine of t is equal to the cube root of 2. So we have now found the cousins and the cosine and sine values for all of most of the community encountered angles in the first quadrant of the unit circle. Right? And let's look at table 1. So we have found the cosine and sine values for all the most common encountered angles in the first quadrant of the unit circle. And sub 1 surprises these values, right? Summarizes these values. So when my angle is 0, I have pi/6 or 30. My angle is 0, it could be pi/4 or 40. My angle is 3, could be cosine of what you call it, cosine of 1, radical 3/2, and so on and so forth. Tell you the truth, me personally, I never memorized this chart. Some professors will tell you that you should memorize this stuff. Right? Not my forte. I like to draw triangles and work out every problem. So that's what I'm going to show y'all to do. But just to say that we actually did it, that's what we got right now. All right. So this is figure 14. All right. So here's some of the common angles in quadrant 1, right? So we have the angle and we have the point that corresponds to the angle for each one. So take a minute, stare at it, take a picture if you want. Kind of is on your formula sheet already, so I understand if you're not hyped to take the picture. Mm-hmm. This is on your trig formula sheet. Yeah, not the algebra one, the other one. This one? Yeah, this one is on the trig formula sheet. Yeah. If you look at the last announcements, I have the formula sheets posted there. I post them in every announcement actually, but you can take a look if you want to see. Yeah. So finding reference angles. So we have discussed finding the sine and cosine for angles in the first quadrant, but what if our angle is in another quadrant? For any given angle in the first quadrant, right, there is an angle in the second quadrant and the same sine value. Because the sine value is the y coordinate of the unit circle, the other angle, right, with the same sine will share the same y value but have the opposite x value. Therefore, right, it's cosine value will be the opposite of the first angle, the angle's cosine value. Likewise, there will be an angle in the fourth quadrant with the same cosine as the original angle, right? The angle with the same cosine will share the same x value, but will have the opportunity to value. Therefore, its wine and video will be opposite of the original Angie's sine value, right? Angle sine value. Lots of diagrams today. So as shown in figure 16, angle alpha has the same sine value as t. The cosine values are opposite. Angle beta has the same cosine value as t. So the sine values are opposite. So sine of t is equal to sine of alpha. Sine of t is equal to negative sine b. And cosine t is equal to negative cosine alpha. And cosine of t is equal to cosine of b, beta. All right. All right. Okay, so recall that an angle's reference angle is the acute angle T formed by the terminal side of the angle T and the horizontal axis, horizontal like this, right? Flat. So a reference angle is always an angle between 0 and 90 or 0 and pi over 2 radians, right? As we can see from this figure, right? For any angle in quadrants 2, 3, or 4, there is a reference angle in quadrant 1. All right? So we got t is equal to basics right there. Then you have two of them on top of each other, etc. Mm-hmm. Given an angle between 0 and 2 pi, find its reference angle. So an angle in the first quadrant is its own reference angle, right? For an angle in the second or third quadrant, right, the refusal angle, is the absolute value of pi minus t, or 180 minus t. For an angle in the fourth quadrant, the reference angle is 2 pi minus t, or 360 minus t. If an angle is less than 0, right? Second. Sorry about that. If an angle is less than 0 or greater than 2 pi, add or subtract 2 pi as many times as needed to find an equivalent angle between 0 and 2 pi. So I want my answers here, right, to be between 0 and 2 pi, or between 0 and 360 degrees. All right. All right. So an angle in the first quadrant is its own reference angle. For an angle in the second or third quadrant, the reference angle is pi minus t, or 180 minus t. For an angle in the fourth quadrant, the reference angle is 2 pi minus t, or 360 minus t, right? And if the angle is less than 0, greater than that, etc. You guys try. I want the reference angle of this. So I'm looking for an answer. This is what, 225 degrees? I'm looking for an answer that's between 0 and 360, but it has to be on the same terminal line that we have here. Hmm? So how can we do this? One simple way is to just take 180 and subtract it from 225. Let's do that. All right. 180 from 225, right? So what is this? This is 5. It's 8. It's 4. And that's it. So 45 degrees. That's here. Questions on this? Finding a reference angle. This is going to become important in the future. Really important in the future. Right. Well, I'm following more specifically. One second. More specifically, I'm following this line right here. That same line. It has to be right on top of that same line. But I need the angle to be something reasonable between, like, say, like 0 and 360. Uh-huh. Oh, down the hole? I'm not sure. Okay. Yeah. I think the Meister ones, some of those take cards. Yeah. It's type sad that we got to talk about vending machines. We got no cafeteria. Let's talk about using reference angles. So now let's take a moment to reconsider the Ferris wheel introduced at the beginning of this section. Suppose a writer snaps a photograph while stopped 20 feet above ground level. The writer then rotates 3/4 of the way around the circle What's the writer's new elevation? So to answer this question, right, such as to answer questions such as this one, we need to evaluate the sine or cosine function of at angles that are greater than 90 degrees or at a negative angle. So reference angles, right, make it possible to evaluate trigonometric functions for angles outside the first quadrant. They can also be used to find the XY coordinates for those angles, right? And then we will use reference angle of the angle of rotation combined with the quadrant in which the terminal side of the angle lies, right? So using reference angles to evaluate trigonometric functions, we can find the cosine and sine of any angle in any quadrant if we know the cosine or sine of its reference angle. The absolute value of the cosine and sine of an angle are the same as those of the reference angle. So the sine depends on the quadrant of the original angle. The cosine will be positive or negative depending on the sign of the x values in that quadrant, and the sine will be positive or negative depending on the sign of the y-axis in the quadrant. Good stuff, good stuff, good stuff, good stuff, good stuff. So using reference angles to find cosine and sine. Angles have cosine and sines with the same absolute value as cosine and sines of their reference angles. All right. The sign positive or negative can be determined from the quadrant of the angle. Okay. It's a little how to. Here's a little how-to. So given an angle in standard position, find the reference angle and the cosine and sine of the original angle. So here's how you do it. Step one, measure the angle between the terminal side of the given angle and the horizontal axis. That is the reference angle, right? Determine the values of the cosine and sine of a reference angle, of the reference angle. Three, give the cosine the same sign as the x values in the quadrant of the original angle. And step four, give the sine the same signs as the y values in the coordinate of the original angle. Cool. All right. All right, so you guys try using reference angles to find the sine and cosine. We want to find the exact value for cosine of 160 and sine of 150 and sine of 150. And then using a reference angle, right? Find cosine of 5 pi over 4 and sine of 5 pi over 4. Try it out, then I'm going to show you how I would do it. All right, so here's how I would do this. I need a pen, 1 second. So I have 150 degrees. I know that 150 is more than 90, but less than 180. So I'm over here, right? So what would I do to figure out what this is? I would take yeah, 180 minus this should be good. 180 minus 150. This leaves me at 30, right? So I'm telling you that this angle inside here is 30 degrees. If that's 30, this is 90, this is 60, right? They said they want cosine, right, of 150. So 150 being this, right? So now, what is cosine of this, right? Remember that cosine is adjacent over hypotenuse. Oh, I forgot to label my legs. Forgot to do that. Opposite of 30-degree angle is 1. Our hypotenuse is always 2, and then this is going to be negative square root 3. Now, again, cosine of 150 is asking you like what is cosine of 30? Right? Cosine of 30. So then it worked down the hall. It worked down the hall. Awesome. All right. So cosine we know is what? Adjacent over hypotenuse. So this would be negative square root 3 over 2. And that's it. Right? Sine. If I'm gonna do sine, sine is opposite over hypotenuse. Sine 150, right? So sine is opposite over hypotenuse. This is just simply 1 over 2. Once you have that reference angle, you can draw the triangle. You can ask any question you want. We can answer it. Very nice and simple, right? Mhm. Hmm? I got you. Got you. No worries, man. Go ahead. Yeah, yeah, it'll be posted. Yeah. So then now we want to do what? Cosine of 5 pi over 4. I'm not gonna lie to you, that's 5 pi over 4. I don't know what that is. I'm more better with my degrees, right? So I want to flip my 5 pi over 4 into degrees. So we have 5 pi over 4 times 180 over pi. Pi's get canceled. 4 goes into 4 once. 4 goes into 180 45 times, I believe. Right? So 5 times 45 is 225. So this is 225 degrees, right? 225 is less than 270, but more than 180. So we in the third quadrant with this. I'm telling you, this whole thing right here is 225, right? What I want to do, I want to kind of pull this back a little bit, right? So I'm going to do what? I like 180 minus this. So 225 minus 180, right? What's that? 45? So right here is 45. So if this is 45, then this is 45. And then what do we have after that? All right. Our legs is going to be what? -1, -1, 2, radical 2. All right. So now I found a cosine. What is sine of 5 pi over 4? Right? So what is that going to equal? I have my triangle already, so I just go straight to opposite over hypotenuse, right? So this is -1. Sorry, so this would be like sine of 45 degrees. Right? Sine is opposite over hypotenuse. This would be -1 over square root 2. Right? All right, using reference angles to find coordinates. Now that we have learned how to find the cosine and sine values for special angles in the first quadrant, we can use symmetry and reference angles to fill in the cosine and sine values for the rest of the special angles on the unit circle, right? And they are shown below. Take time to learn x coordinates and all major angles in the first quadrant. Some of you might recognize this. Right. So take a picture, write it down, although it is in your formula sheet. It's not colored like this, so enjoy. How's everything, man? Good? Appreciate it, man.
Super struggle word.
Gotcha.
It's it only call.
Leave this up for a minute in case anybody wants to take a picture and take a look at it. Literally, this one picture has all the answers to your homework. So in addition to learning the values of special angles, we can use reference angles to find XY coordinates of any point on the unit circle using what we know of reference angles along with the identity. So x equals cosine t and y equals sine t. First, right, we find the reference angle corresponding to the given angle. Then we take the sine and cosine values of the reference angle and give them the sine corresponding to the y and x values of the quadrant. All right, so given the angle of a point on a circle and the radius of the circle, appreciate it, man. Thank you. All right. Um, find the XY coordinates of that point. So here's how you do it. Step one, find the reference angle by measuring the smallest angle to the x-axis. Step two, find the cosine and sine of the reference angle. Step three, determine the appropriate signs for x and y in the given quadrant. Look at an example. So using a unit circle to find the coordinates, you want to find the coordinates of the point on the unit circle at an angle of 7 pi over 6. Not gonna lie, I don't know what that is, so I got to convert it. 7 pi over 6. I'm gonna multiply that by 180 over pi. Let's see what I get. Pi's cancel, 6 and a 1. I think this is 30. Um, uh, 6 and 6 is 12. 30, yeah, that's good. But then now we have what, 210 degrees. Now 210 is more than 180, less than 270, right? So third quadrant, right? Here's the thing. All of this is 210. I want to know the reference angle on the inside. So I'm going to do 210 minus 180. And I get, what's that, 30? Right? So this is 30 degrees here. If that's 30, that's 90. This is 60. Right? And then opposite the 30 is -1. Opposite the 60 is negative square root 3. And then 2. So now, which coordinate did I find? So this coordinate here. My x value is negative square root 3. And my y value is what? -1. And that's the point. Questions on this? There's homework on this too. But it's not much though. It's like 5 questions. The last ones that just got posted.
Why the y -1? About relation.
The 2 is the hypotenuse. That's different. Yeah. X is the horizontal, like going across like that, and y is like the vertical of the triangle. You know what? I'm bugging. Hold on. Cosine, right? Because we said this earlier. I'm bugging 1 second. This is x and this is y, right? We said that x was what? Cosine of our reference angle, which would be 30 degrees. Well, cosine is what? Adjacent over hypotenuse, right? So this is negative square root 3 over 2. That's this one, negative square root 3 over 2. We said that y was our sine. Let's see, 30 degrees, right? So that's like what? Opposite over hypotenuse. So that's negative 1 over 2. That's the real point. I'm sorry, I made a mistake quickly. So this next thing is actually really, really interesting. Really, really interesting. I personally didn't know this, but I want to share this with y'all. All right. So a wheelchair ramp that meets the standards of the ADA Accessibility Americans with Disabilities Act must make an angle with the ground whose tangent is 1 over 12 or less, regardless of its length. A tangent represents a ratio. So this means that for every 1 inch of rise, the ramp must have 12 inches of run. All right, real interesting. Trigonometric functions allow us to specify the shapes and proportions of objects independent of exact dimensions. So we have already defined the sine and cosine functions of an angle. Though the sine and cosine are the trigonometric functions most often used, there are 4 others, right? Together, they make up the set of 6 trigonometric functions, right? In this section, we will investigate the remaining functions, all right? So I know we were asking about tan before. Let's get to it now. Let's get to it now. All right. So finding exact values of the trigonometric functions, secant, cosecant, tangent, and cotangent, right? So to define the remaining functions, we will once again draw a unit circle with the point xy corresponding to the angle of t, as shown in this figure, right? As with the sine and cosine, we can use the xy coordinates to find the other functions, right? The first function we will define is the tangent. So the tangent of an angle is the ratio of the y value to the x value of the corresponding point on the unit circle. The tangent of angle T is equal to y over x, where x does not equal 0. Because the y value is equal to the sine of t and the x value is equal to the cosine of t, the tangent of angle t can also be written and defined as sine of t over cosine of t, where cosine of t cannot equal 0. So the tangent function is abbreviated as tan. The remaining 3 functions can all be expressed as reciprocals of functions we have already defined. All right, good stuff. So the secant function is the reciprocal of the cosine function, right? In figure 1 that we had up here, right? The secant of angle t is equal to 1 over cosine of t, which is equal to 1 over x. The secant function is abbreviated as sec, S-E-C, right? The cotangent function is the reciprocal of the cotangent function. So in figure 1, the cotangent function, the cotangent of angle t is equal to cosine t over sine t or x over y, right? Where, of course, y cannot equal 0. right? The cotangent function is abbreviated as cot, C-O-T, right? The cosecant function is the reciprocal of the sine function. So in a figure, the cosecant of angle t is equal to 1 over sine t, which is equal to 1 over y, where y does not equal 0. The cosecant function is abbreviated as CSC. I don't know how to say that. CSC. All right? Cosecant. All right? If it's okay, I just want to sum this up a little bit. All right, just want to make it nice and pretty for everybody. There you go. So tangent, secant, cosecant, and cotangent function. If t is a real number and xy is a point where the terminal side of the angle of t, radians, intercepts the unit circle, then tan of t is equal to y over x, secant of t is equal to 1 over x, cosecant of t is equal to 1 over y, cotangent of t is equal to x over y. And just to recap real quick, right? X is equal to the cosine of t, right? And y is equal to the sine of t, right? Just in case you're wondering what is x, what is y in this. Let's look at an example. So here in this example, we're finding the trigonometric functions from a point on the unit circle. So the point is going to be negative square root 3 over 2 and 1/2, right? It's on the circle. Boom. There it is. Nice and pretty for us, right? So we want to find all the trigonometric functions, right? We want to find sine, cosine, tangent, secant, cosecant, cotangent. We want to find everything, right? So easiest way to do this, in my opinion, let's complete the triangle here, right? So for me, this is the second quadrant, right? They're calling all of that T, but I call this T right here, right? And I see, right? My X, let me say it like this, X is equal to cosine of T. And remember, cosine is what? Adjacent over hypotenuse, right? So what will be the adjacent here? Negative square root 3, hypotenuse 2, right? So what do I know after that? I know that this must be positive 1. And now I can find everything. What you want to know? You want to know cosine of t? Got you, right? Cosine of t, adjacent over hypotenuse. The adjacent is negative square root 3 over 2. You want to know what? Sine of t? Light work, right? Sine is opposite over hypotenuse, right? So that's like what? 1 over 2, right? You want to know tangent of t? Easy. Tan is what? Opposite over adjacent. So that's just going to be 1 over negative square root 3. Y'all know I can't leave it like that with the radicals. So I got to, fix it up. So multiply by radical 3 over radical 3. So this is what? Negative radical 3 over 3. Right? Then we're going to have what? What's another one? You want to know the secant? Right? Secant of t. Now we remember secant is 1 over cosine, right? So 1 over the cosine of t. That means that all I have to do is just flip the cosine of t to that answer that I got there. So this is what? Negative 2 over square root 3, right? But I can't leave it like that, right? Because it got a radical in the denominator. So I got to multiply this by radical 3. Radical 3, final answer. Negative 2 radical 3 over 3, right? That's the secant, right? Let's do the cosecant. Now we know cosecant is 1 over sine of t, right? So this is what? This is going to be 1 over, let's say 1 over 2. You already know keep, change, flip. Just to recap on how to do this, it'll be 1 times 2 over 1. Call that 2. All right?
So,
Go ahead.
-2 times -2? Just looking, just taking negative side.
It's the negative is on the radical 3. It's not on the 2. The 2 is positive actually.
No, I mean like, look,
Yeah, I'm just carrying it to the top. I like to write my negatives on top. It doesn't matter if you write the negative on top, bottom, or on the side. I guess the side makes more logical sense, but I like to put my negatives on top, you know. All right, last one. Let's do the cotangent, right? Cotangent right here of t, right? We already know that this is going to be what? 1 over tan of t. And what was tan? Tan was 1 over negative square root 3. All we got to do is flip that. So this is going to be what? Negative square root 3. And that's it. Questions on this? Go ahead. No. The calculator is going to give you some decimal answers. Like, I just want the fraction. Nah. To be honest with you, this particular section, the calculator will make it harder for you. Like, because all I'm looking for is a simple little fraction. This over this. That's it. You know? Nice and easy. Hmm? What happened? That's all that is. That's all the trigonometric functions right there. Thursday. Yeah. The whole thing. Yeah.
You don't have, any more exam, right?
Nah. I feel like we don't have enough time. Let me just come back up here real quick. This was so this situation is when I had a point, right? Well, watch this other trick right here. Here's another example. So let's say that I'm given an angle. A little bit different. I'm given an angle, and from that angle, I want to do all of the trigonometric identities or whatever, right? Functions. So our angle is what? T equals pi over 6. Now you guys know I don't know what that is, right? Let's change that over. So this is going to be times 180 over pi. Pi's will cancel. 6 goes into 6, 1. 6 goes into 180, I think 30. 6 is 12. Yep. Okay, so now we have what? 30 degrees. I could work with 30 degrees now, right? That's simple right there, right? So we have our quadrant right here. That's going to be on the first quadrant. Bam. Right? There we go. There's our triangle. Right? So I'm telling you that right here, this reference angle, that's 30 degrees. That's 90. That means that this is 60 degrees, right? Let me get my little circle right there. There we go. There we go. Right? So now just fill it in, right? Opposite the 30 degree is 1, right? Opposite the 60 degree is radical 3, and our hypotenuse is 2, right? We remember our special right triangles from Math 28, right? Simple. Boom, right? We could give them everything. What they want. You want sine of t? I got you. I'm sorry, sine of 30. Technically, you know what? Let me not write 30. It's technically pi over 6, right? Let's keep it straight, right? It's pi over 6. But we know that pi over 6 is just 30, right? There we go, right? So sine of pi over 6, sine is what? Opposite over hypotenuse. It's just 1/2. I'm done. Right? You want cosine? I got you. Cosine pi over 6. Let's do it. Right? Cosine we know is adjacent over hypotenuse, right? So what is that? That's radical 3 over 2. We good. Right? How about tan? Y'all want tan? Let's get tan, right? No sun out right now, but we can still do tan, right? This is pi over 6 is equal to, right? Tan is what? Opposite over adjacent, right? Opposite is 1 over the adjacent radical 3, but you know I can't leave that radical in the denominator, right? Rationalize it. Let's multiply it by radical 3. Radical 3, call that a day. This is radical 3 over positive 3, done, right? Let's keep it going. Let's keep it going. You want cosecant? All right, so cosecant of pi over 6, right? You already know cosecant is 1 over sine, right? So it's just going to be 1 over sine pi over 6, right? Boom. So all that means I just got to flip the sine answer, right? So this becomes what? 2 over 1. How about secant? Secant of pi over 6, right? Remember, secant is what? 1 over cosine of pi over 6, right? So just flip your cosine answer. This is going to be what? 2 square root 3 over 3, right? I didn't have space, so that's why I just kind of did it in my head, right? What about the cotan? Cotan is wasn't mentioned at all, right? Pi over 6, that's just 1 over the tan, right? So this is going to be what? Radical 3 over 1. Easy peasy beautiful, right? All right. I'm going a little bit fast with this because you guys have all this information on your formula sheet. You do not have to memorize it. It's right there, written out. Some people have seen the formula sheet before, right? Mhm. All right. I know some people's like, nah, I'm not in the whole drawing triangle thing. I want to memorize it. I got y'all, man. I got y'all. Not my favorite, but all right, here we go. Here we go. Here we go. I'm gonna just give it to y'all. I'm gonna just give it to y'all. If you really want to memorize it, go ahead. Here you go, right here, right? So because we know the sine and cosine values for the common first quadrant angles, we can find the other function values for those angles as well by setting x equal to the cosine and y equal to the sine, and then using the definition of tangent, secant, cosecant, and cotangent, right? Here's the result. Lord help me. All right. Those of you that want something to memorize, here you go. I'll leave it up for like a minute. Oh, Lord. Here we go. It's too much. It's too much right here for me. But all right, here we go. So when your angle is 0, right? Cosine is 1, sine is 0, tangent is 0, secant is 1, cosecant undefined, cotangent undefined. Because remember, we can't divide by 0, right? If it was pi over 6 or 30 degrees, here it goes. Cosine is radical 3 over 2. Sine is 1/2. Tangent is radical 3 over 3. Secant is 2 radical 3 over 3. Cosecant 2. Cotangent radical 3, etc. You guys get the idea, right? I don't do this, but if y'all want to, you have my blessing. No. Well, it is. It's in the unit circle. Right? So it's like, why memorize it? But whatever. To be honest with you, like that's the answer to all your homework right there. You can just type those over and over, and then the whole homework is done. Yeah, yeah. You have it. I don't have a copy, but y'all have y'all formula sheets. Y'all know. Hmm. The formula sheet, yeah. Not the algebra one, the other one, the second one. Yeah, yeah, yeah. Yeah. They all posted. You guys can download it anytime, print it anytime. I recommend using it to do your homework. Just saying, you get some good practice that way. Mhm.
For the exam done, he said, right?
No, you can use it on the exam. Yeah, yeah. All right, so using reference angles to evaluate tangent, secant, cosecant, and cotangent. So we can evaluate trigonometric functions of angles outside the first quadrant using reference angles, as we have already done with the sine and cosine functions. The procedure is the same. Find the reference angle formed by the terminal side of the given angle with the horizontal axis. The trigonometric function values for the original angle will be the same as those for the reference angle, except for the positive or negative signs, which is determined by the X and Y values in the original quadrant. Figure 4 shows which functions are positive in which quadrants, right? So to help us remember which of the 6 trigonometric functions are positive in each quadrant, we can use a mnemonic phrase, a smart trig class, right? Some people say all students take calculus, right? Personally, I don't like that one because it's not true. You know, it's not all students don't take calculus. It's not true. But a smart trig class, yay, right? Y'all come to two and I'll tell you another one that's even better, right? So each of the 4 words in the phrase corresponds to one of the 4 quadrants, starting with quadrant 1 and rotating counterclockwise in quadrant 1, which is A, all of the 6 trigonometric functions are positive. In quadrant 2, right, smart, only sine and its reciprocal function cosecant are positive. In quadrant 3, trig, only tangent and its reciprocal function cotangent are positive. Finally, in quadrant 4, right, class, only cosine and its reciprocal function secant are positive, right? So remember that, right? All that good stuff. I know some of y'all just looked at all the words and was like, yo, I don't understand. Yo, here you go. Here you go right here. This is what I just said in the words. All right. First quadrant, all of them. Second quadrant, sine. Third quadrant, tan. Fourth quadrant, cosine. Right? Gotcha. Let me give y'all a little how-to real quick. Oh, a little too fast. All right, let me give y'all a little how-to real quick. So given an angle not in the first quadrant, use the reference angles to find all 6 trigonometric functions. So here's how we do it. First, we measure the angle formed by the terminal side of the given angle and the horizontal axis. This is the reference angle, right? Reference angle is important, right? Evaluate the function at the reference angle and then observe the quadrant where the terminal side of the original angle is located. Then based on the quadrant, determine whether the output is positive or negative, all right? That's it, that's it, that's it. Literally, your homework is asking you, like, yo, what quadrant is this in? First, second, third, fourth. That's it. You know, it'll take you 2 seconds. Y'all can do it right now if y'all want. It's only do like 2 questions. You know. Oh my gosh, here we go. I gotta stop giving myself hard examples. All right. So look, use reference angles to find all 6 trigonometric functions of negative 5 pi over 6. Oh Lord. Here we go. Here we go. Here we go. Because y'all know I don't know this radian stuff, right? So we have negative 5 pi over 6. What we gonna do? Multiply this by what? 180 over pi, right? Let's kill the pi's. 6 goes into 6, 6 goes into 180, I think 30 times. Let me think about that. 6 and 6 is 12. 6, yep, that sounds about right. Okay, so this is going to be what? Negative 150 degrees. All right, check this out. Check this out. Check this out. This is actually a good example right here because we never dealt with a negative before, right? So check out the negative right here. Remember, negative, we going backwards, right? Counterclockwise. So this is 90 right here. This is negative 90. This is my negative 180, right? This is my negative 270. And then this is my 0 and my negative 360. There we go. So I want negative 150, right? Negative 150 is going to be right over here, right? There we go, right? So boom. That's my negative 150 degrees right there. But you know that's not my reference angle though, right? Right? So how can I fix this? How can I fix this, right? Well, I could add 360 to it. Let's see what happens if I do that. What is 360 plus a negative 150? Let's see what that is, right? So this is 0, this is 1, this is 2. That's 210. All right, so I know that if I go all the way here, that's going to be 210. But still, that's not the reference that I want. That probably wasn't smart. That's probably wasn't smart. How about, what else could I have done? I mean, that's fine. So what I found, right? Technically speaking, I found a coterminal angle, right? By adding 360 to it, I found what's called a coterminal angle. But what I really want is I want a reference angle, right? I want a reference angle. So 210, if I take 210, subtract 180 from that, there we go. Now I have 30 degrees. Now I'm in business. Look at this. I'm in business right here. 30 degrees reference angle, making my triangle. So that means that this is 60 degrees right here. Boom. Got my 90 right there. And then you remember, we all remember our special right triangles, right? Opposite the 30 is going to be -1. Opposite the 60, negative radical 3. And the hypotenuse is 2. This question is done. That's it, right? Now all I gotta do is go right through them. Let me keep it good with the radians, right? So let's do cosine. Cosine of negative 5 pi over 6, right? Cosine is what? Adjacent over hypotenuse. This is what? Negative square root 3 over the hypotenuse 2, right? Done, right? Sine. Sine negative 5 pi over 6. Sine is what again? Sine is opposite over hypotenuse. What is this? -1 over 2. How about tan? Negative 5 pi over 6. Let me see what that is, right? Remember, tan is opposite over adjacent. So opposite, -1, right? Over the adjacent, negative radical 3, right? So what is that? That's radical 3 over 3. Boom, right? And then you already know what's going to happen, right? When I say cosecant, in no particular order. Cosecant just came to my mind. -5 pi over 6, right? Remember, cosecant is 1 over sine, so I'm just going to flip the sign. This is what? -2. Secant, -5 pi over 6. Remember, secant is what? 1 over cosine. I'm just going to flip the cosine answer. So what is that? That's 2, -2 radical 3 over 3, right? Then we have what? Cotangent, right? So when I have cotangent, what's that? Right? Of -5 pi over 6. I forgot to write that, right? What is that? We're just gonna flip the tangent answer, right? So what is this? This is just gonna be radical 3. And that's it. Easy, right? Draw the triangle, right? SOHCAHTOA that joint, bop, 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 and we're good to go. All right? All Math 28 stuff right here, man. Nothing new here, nothing new here. I'm gonna let y'all know when we get to something new. All right. So check this out. So now we're going to talk about using even and odd trigonometric functions, all right? So to be able to use our 6 trigonometric functions freely with both positive and negative angle inputs, we should examine how each function treats a negative input. As it turns out, there is an important difference among the functions in this regard, all right? Now, if you draw your angles on the unit circle like I do and stuff. Kind of don't need this, but let's go through it real quick. Let's just humor me for a little bit. It's a nice little recap also. We're gonna start off with what we started off earlier in the class with. All right. So consider the function, right? F of x is equal to x squared, right? As shown in this figure below. The graph of the function is symmetrical about the y-axis. All along the curve, any 2 points with opposite x values have the same function values. This matches the result of the calculation. So 4 squared is equal to negative 4 squared, and negative 5 squared is equal to 5 squared, and so on and so forth, right? So f of x is equal to x squared is an even function, a function such that two inputs that are opposites have the same output. So f of negative x is equal to f of x. This is what it means to be an even function, right? Remember this, all right? This was earlier in the class, all right? Let's recap what an odd function is real quick, all right? Let's recap. Nice little, nice little refresher, all right? Not like we have a final coming up or anything, all right? So now consider the function f of x is equal to x cubed, right? Shown in this figure below, right? The graph is not symmetrical about the y-axis. All along the graph, any 2 points with opposite x values also have opposite y values. So f of x is equal to x cubed is an odd function, one such that two inputs that are opposites have outputs that are also opposites. So that means that f of negative x is equal to negative f of x, right? So when you plug in a negative x value, you're getting out a negative y value. That's the opposite right there, right? All right, let's keep talking. Let's keep talking, right? So we can test whether a trigonometric function is even or odd by drawing a unit circle with a positive and a negative angle as in this figure below. The sine of the positive angle is y. The sine of the negative angle is negative y. The sine function then is an odd function, right? So we can test each of the 6 trigonometric functions in this fashion, right? And the result will be shown. So here we go. I got y'all all tested and proven, right? Check this out, check this out, check this out, check this out. Here we go. 1 second. Boop, 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 boop. Commercial break. All right. For dry, red eyes, clear eyes is awesome. All right, anyway. So here we go. I have sine of t is equal to y, right? And then let's say I plug in a negative angle right here, I get out a negative y. So sine of t does not equal sine of negative t, right? Odd, right? Secant of t is equal to 1 over x. If I plug in a negative t, I get 1 over x. So secant of t is equal to secant of negative t. That's an even function, the secant, right? Let's talk about cosine. So cosine of t is equal to x. Cosine of negative t is also equal to x. So cosine of t is equal to cosine of negative t. So cosine is an even function, right? Cosecant of t, right, is equal to 1 over y. Cosecant of negative t is equal to 1 over negative y, where cosecant of t does not equal cosecant of negative t, right? That is an odd function, all right? Tan of t is equal to y over x. Tan of negative t is equal to negative y over x. Tan of t does not equal tan of negative t. That means that tan is a odd function, right? Last but not least, cotangent of t is equal to x over y. Cotangent of negative t is equal to x over negative y. Therefore, cotangent of t does not equal the cotangent of negative t. Cotangent is an odd function. All right? There we go, there we go, there we go. All right. I know some of y'all don't like that white background. I got y'all. I got y'all. I'll be thinking ahead for y'all, man. So even in odd trigonometric functions, here you go right here, right? Let me make that a little bit bigger, right? Projector can only do but so much, right? So an even function is one in which f of negative x is equal to f of x, And an odd function is one in which f of negative x equals negative f of x. So cosine and secant are even functions, right? So cosine of negative t is equal to cosine of t, and secant of negative t is equal to secant of t. Sine, tangent, cosecant, and cotangent are all odd functions, right? So sine of negative t is equal to negative sine of t. Tan of negative t is equal to negative tan of t. Cosecant of negative t is equal to negative cosecant of t. And cotangent of negative t is equal to negative cotangent of t. All right. Good stuff, good stuff, good stuff. So using even and odd properties of trigonometric functions, if the secant of angle t is 2, what is the secant of negative t, right? Let's look up here, right? Secant of t is 2. So what's secant of negative t, right? It's also going to be 2. Why? Because it is an even function. That's simple, right? Right? All blessings, all blessings. Good stuff. Oh, shoot. Here we go. This is the good stuff right here. This is my favorite part. My favorite part right here. I know y'all gonna hate this, but this is my favorite part. All right. So recognizing and using fundamental identities. So we have explored a number of properties of trigonometric functions. Now we can take the relationships a step further and derive some fundamental identities. Identities are statements that are true for all values of the input on which they are defined. Usually, identities can be derived from definitions and relationships we already know. For example, the Pythagorean identity we learned earlier was derived from the Pythagorean theorem and the definitions of sine and cosine, right? Oh, check this out. Check this out. I'm about to make this mad simple. Mad simple. Y'all gonna love this. Y'all gonna love this right here. This is the sauce right here. This is sauce. Nobody else knows this, man. Nobody else shares this, but I'm gonna share it with y'all. I'm gonna share it with y'all. All right. So fundamental identities right here. So we can derive some useful identities from 6 trigonometric functions. The other 4 trigonometric functions can be related back to the sine and cosine functions using these basic relationships right here. So check this out. Tan is equal to sine over cosine. Secant is equal to 1 over cosine. Cosecant is equal to 1 over sine. Cotangent equals to 1 over tan, which becomes what? Cosine over sine, all right? This is the sauce right here. All right? There we go. So check this question out real quick, right? So we want to use the identities, the ones that we just spoke about, to answer these questions, right? So let's look at A. A says that given sine of 45 degrees, so sine of 45 degrees, right, is equal to radical 2 over 2, right? And cosine of 45 degrees is equal to radical 2 over 2. They want to know what's tan, right? What's tan of 45 degrees, right? But we already know that tan is equal to what? Sine over cosine, right? So you already know what's going to happen. This is going to be sine of 45 degrees, right? Over cosine of 45 degrees. It's that simple, right? So then this is what? This is radical 2 over 2 divided by radical 2 over 2. Now, somebody help me. Anytime I divide something by itself, what do I get? 1, right? That's it. That's the answer. I'm done. That's simple, right? Let's look at the second one right here. I'm gonna change up my color for this one though. This is gonna be a little messy. So I have sine of 5 pi over 6 is equal to 1/2. I have cosine of 5 pi over 6 is equal to negative square root 3 over 2. All right. Now I want to know, what is secant of 5 pi over 6? Well, it's not so bad because I know that secant is just 1 over cosine, right? So this is 1 over cosine 5 pi over 6. So what does that mean? It literally means that this is 1 over negative square root 3 over 2. You already know, keep, change, flip, all that good stuff, right? So this is negative, what, 2 over square root 3. But you know I can't leave it like that, right? Got to simplify this. So let's multiply by radical 3 over radical 3. So this becomes what? Negative 2 radical 3 all over 3. Boom, that's my answer. I'm done. Not bad, right? See, it's easier to just manipulate the fractions than it is to just like throw it in the calculator, because calculator will give you some long decimal thing. Maybe it's right, maybe it's not right. Who knows? You know? Oh, now we get into the good stuff right here. This is the juicy stuff right here. Yeah, that's my favorite right here. You're building up to it. You're building up to it. All right, so this is using identities to simplify trigonometric expressions. All right. So boom, telling you right out, I got secant of t is equal to tan. Excuse me, secant of t over tan of t, right? And I want to simplify this. Don't fret, don't fret. You know exactly what to do. Secant is what? Is 1 over cosine of t, right? Over tan. What's tan again? Tan is sine over cosine, right? So this is sine t over cosine t. It's that simple, right? You have a fraction divided by a fraction. Keep, change, flip. What's this going to be? This is 1 over cosine of t, right? Times, flip the bottom, cosine of t over sine of t, right? Multiply straight across. You already know this is going to cancel out. This is just 1 over sine of t. To be honest with you, I would take this answer right here, but you know that they want you to go a step further, right? 1 over sine is the same thing as what? Cosecant, right? So this is cosecant t. There you go. All right. Simple. Right? Simple, simple, simple. Oh man. I don't tell many people about this secret, but I'm sharing it with y'all. Giving y'all the sauce right now. All right. Let's talk about alternate forms of the Pythagorean identity, right? So we can use these fundamental identities to derive alternate forms of the Pythagorean identity. Cosine squared t plus sine squared t is equal to 1. Remember that, right? That's the most important one of all, right? One form is obtained by dividing both sides by cosine squared of t, right? So divide by cosine squared of t on both sides, you get 1 plus tan squared t is equal to secant squared t. Do I memorize that? No. Cosine squared plus sine squared equals 1. That's all I memorize, right? The other form is obtained by dividing both sides by sine squared t. Divide everything by sine squared t, you get cotan squared t plus 1 is equal to cosecant squared t. Cool, right? All you got to remember, cosine squared plus sine squared equals 1, right? That's the main one right there. But in case you're trying to memorize, I got you. This is it right here. Alternate forms of the Pythagorean identity. 1 plus tan squared t is equal to secant squared t. And cotangent squared t plus 1 is equal to cosecant squared t. There you go. Let's take a look at an example. I'm going to unpack this the same way, nice and simple, right? So if cosine of t is equal to 12 over 13, got it, right? And t is in the fourth quadrant as shown in the picture below, find the value of the 5 trigonometric functions, right? Not bad, not bad, not bad, right? So here we go. Let me redraw it down here, right? So I'm telling you, I'm right down here. I'm in the fourth quadrant, right? Fourth quadrant. This is t right here, right? And cosine of t, right? So x equals cosine of t is equal to 12 over 13. Now we know that cosine is what? Adjacent over hypotenuse. So what's my adjacent? 12. What's my hypotenuse? 13. All I got to do is figure out that other side, right? Figure out that y side, right? How could I figure that out? Pythagorean theorem. Keep it simple, right? A squared plus b squared equals c squared, right? So what's this going to be? This is going to be 12 squared plus b squared equals 13 squared, right? 144 plus b squared is equal to 169. Subtract 144. Do to one side, you know you got to do to the other, right? So now what do I have? I have b squared is equal to 9 minus 4. What's that? 5. And then 6 minus 4. What's that? 2. So b squared is equal to 25 square root both sides. So we know that b is equal to 5. But not just any 5. B is equal to -5. Right? The question's done. That's it. Right? I have cosine. They said they wanted sine, right? So look, sine of t is equal to what? Opposite over hypotenuse. What's that? -5 over 13. Done. Right? They said they wanted tan. I got you. Tan. What's tan? Opposite over adjacent, right? So what's that? -5 over 12. Done. Right? They said they want cotangent. No problem, right? Cotangent of t, right? Just let me erase that tilde, right? Just flip the tan. Keep it simple. -12 over 5. Done. They said they want cosecant, right? Cosecant, easy, right? Of t. I forgot the t, right? Is equal to what? Just flip the sign, right? What's that? -13 over 5. Done. Right? What's the one I'm missing? Secant, right? Secant is going to be what? 1 over cosine, right? What was my cosine again? I'm not even going to scroll up to look at it, right? Cosine is what? Adjacent over hypotenuse, which is 12 over 13. Just flip it, right? Just flip it, right? So this is what? 13 over 12. Done. Easy, right? Can't even beat that, right? And I know I'm going a little bit fast. It's on your formula sheet, so you got to memorize it. All right, it's right there. Hmm? No, it's right there. It's on your formula sheet. You see that big circle? That's the whole trigonometric section right there. Done. Y'all good to go. All right. So as we discussed in the chapter opening, right, a function that repeats its value in regular intervals is known as a periodic function, right? The trigonometric functions are periodic for the 4 trigonometric functions sine, cosine, cosecant, and secant. A revolution of one cycle is, or 2 pi, will result in the same output for these functions. And for tangent and cotangent, only a half of a revolution will result in the same output. Other functions can also be periodic. For example, the length of months repeat every 4 years, right? So let's say if X represents the length of time measured in years and F of X represents the number of days in February, right? Then F of X plus 4 would be equal to F of X. This pattern repeats over and over through time. In other words, every 4 years, February is guaranteed to have the same number of days as it did 4 years earlier. So positive number 4 is the smallest positive number that satisfies the condition and is called the period, right? So a period is the shortest interval over which a function completes one full cycle, right? In this example, the period is 4 and represents the time it takes for us to be certain February has the same number of days. All right. Good stuff, good stuff, good stuff. So let's talk about the period of a function, right? So the period P of a repeating function f is the number representing the interval such that f of x plus p is equal to f of x for any value of x. The period of cosine, sine, secant, and cosecant, functions is 2 pi. The period of the tangent and cotangent function is pi. Okay? Let's look at an example real quick. Oh my gosh, look how easy this is. This is done already. Question's done, right? Look at this. X is equal to what? Cosine of t, which is equal to negative 1 over 2, right? Y is equal to sine of t, which is equal to negative square root 3 over 2, right? I didn't even read the instructions. Hold up. Find the value of the 6 geometric functions of angle t. They already gave me 2. They already gave me 2. I ain't even do nothing for that, right? But check this out. Let's get tricky with this. Let's get tricky with this, right? So tan of t, we know is what? Y over x, right? So this is what? Negative square root 3 over 2 divided by negative 1 over 2. Now, a negative divided by a negative, we know is positive, which just don't seem right. Hold up, hold up. Something wrong here. Something wrong here. No, that's right. I forgot. Tangent is positive in the third quadrant. My mistake, my mistake, my mistake. All right, so here we go. I got radical 3 over 2 times, keep change flip, 2 over 1. This cancels out. This is just what? Radical 3. Boom. Look at that. I got 3 of them. I didn't even do nothing for that, right? I didn't even use the graph that much, right? All right, so let's keep it going. Let's keep it going. How about cosecant? I don't know why I said cosecant, just popped in my head, right? Cosecant we know is just 1 over sine, right? Right? This is 1 over sine. Keep it simple, right? So 1 over sine, I'm going to flip the answer I got there. This is what? Negative 2, right? Radical 3 over 3. Simple, right? How about the secant? Oh, here we go. Is that going to be harder? No, it's not. That's just 1 over cosine, right? So we're just going to flip the cosine answer. So what's that? Negative 2, done, right? What about the cotangent? Cotangent right here, right? We know it's going to be positive. But all you're going to do is what? You're just going to flip the tangent answer, which is radical 3 over 1. So what's that going to be? That's just going to be radical 3 over 3, right? Keep it simple. Keep it simple. All right? No stress over here. No stress. Yeah, we about to fly through this. Yeah. I feel like we kind of get how to do this. So I want to jump this next example. Next example is literally the same thing. It's just that they instead of the graph, they just gave you the points. but it did it the same way that I just did that. All right. Let's get back into it. Some good stuff right here. All right. So we have previously defined the sine and cosine of an angle in terms of the coordinates of a point on the unit circle intersected by the terminal side of the angle. So cosine of t is equal to x, sine of t is equal to y. In this section, we will see another way to define trigonometric functions using properties of right triangles. Oh, yeah, here we go. It's my favorite right here. It's the sauce. But to be honest with you, it's not really a big secret because y'all seen this all in 28, what I'm about to show y'all. Ain't nothing new here, you know? So using right triangles to evaluate trigonometric functions. So in earlier sections, we use a unit circle to define the trigonometric functions. In this section, we will extend those definitions so that we can apply them to right triangles. All right. So the value of sine or cosine functions of t, right, is its value of t radians. First, we need to create our right triangle. So shows so figure one, right, shows a point on a unit circle of radius 1. If we drop a vertical line segment, right, from xy, right, to the x-axis right here, right, we have a right triangle whose vertical, right, side has length y and whose horizontal side has length x. We can use this right triangle to redefine, right, sine, cosine, and the other trigonometric functions as ratios of the sides of the right triangle, right? Excellent, excellent, excellent. All right. So again, y'all probably seen this all already. Just going through the motions. But we're gonna see something new today, though. I'm gonna show y'all, right? So we know that cosine of t is equal to x over 1, which is equal to x, right? And likewise, we know that sine of t is equal to y over 1, which is y, right? These ratios still apply to the sides of the right triangle when no unit circle is involved and when the triangle is not in a standard position, right? And is not being graphed using the XY coordinates. To be able to use these ratios freely, we will give the sides more general names. Instead of X, we will call the side between the given angle and the right angle the adjacent side of angle T. Adjacent means next to, right? Instead of the Y, right, we will call the side most distant from the given angle the opposite side of angle T, right? And instead of 1, we will call that side of, we will call the side of the right triangle opposite the right angle the hypotenuse. So here you go. Here's the right triangle, right? Angle T is right here. Adjacent is next to the angle, right? Opposite is away from it. And the hypotenuse is the diagonal, right? Nothing new here, right? We all know this. Let's keep it moving. Let's keep it moving. All right. Let's keep it moving. All right. Understanding right triangle relationships, right? So given a right triangle with an acute angle of t, sine of t is equal to opposite over hypotenuse, cosine of t is equal to adjacent over hypotenuse, tan of t is equal to opposite over adjacent. Right from your formula sheet. Boom. Right? A common mnemonic for remembering these relationships is SOHCAHTOA, right? Formed from the first letter of sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent, right? Good stuff, good stuff. All right. Let's keep it moving. So given the side lengths of a right triangle and one of the acute angles, find the sine, cosine, and tangent of that angle. So to find the sine as a ratio of the opposite side to the hypotenuse, find the cosine as a ratio of the adjacent side to the hypotenuse, find the tangent as a ratio of the opposite side to the adjacent side, all right? Again, nothing new here. We all knew that, all right? All right, real quick, just humor me. What's cosine of alpha here? Just blurt it out. What's the answer? What over what? Cosine alpha equals, what is it? Yep. So give me the numbers real quick. See? Over. Perfect. That's it. All right. We good. We know how to do this. All right. Again, all on your formula sheet. All right, so relating angles and their functions. So when working with right triangles, the same rules apply regardless of the orientation of the triangle. In fact, we can evaluate the 6 trigonometric functions of either of the 2 acute angles in the triangle in figure 5, right? The side opposite one acute angle is the side adjacent to the other acute angle and vice versa, all right? So here we go. So if I'm talking about angle alpha, opposite angle alpha is away from it, adjacent is next to it, right? If I'm talking about angle beta, opposite from it is this side leg and adjacent is next to it, right? So we'll be asked to find all 6 trigonometric functions for a given angle in a triangle. Our strategy is to find the sine, cosine, and tangent of the angles first, right? Then we can find the other trigonometric functions easily because we know that the reciprocal of sine is cosecant, the reciprocal of cosine is secant, and the reciprocal of tangent is cotangent, right? Damn, we ain't even got to memorize that. We on fire right now. We on fire. We on fire. All right. All right. But I know you want to hear it again, so I got you. I got you. I got you right here. Let me give you a little how-to. All right. So given the side lengths of the right triangle, we want to evaluate the 6 trigonometric functions of one of the acute angles. Here's how you do it. Step 1, if needed, draw the right triangle and label the angles provided. Step 2, identify the angle, the adjacent side, the side opposite the angle, and the hypotenuse of the right triangle. Step 3, find the required function. Sine as a ratio of the opposite over the hypotenuse, cosine as a ratio of the adjacent over the hypotenuse, tangent as a ratio of the opposite to the adjacent, secant as a ratio of the hypotenuse to the adjacent, cosecant as a ratio of the hypotenuse to the opposite side, cotangent as a ratio of the adjacent side to the opposite side. All right? Good stuff, good stuff, good stuff, good stuff. All right. So bam, I feel like we know that already. Da da da. Yeah, let's get to this. This is what I really want to talk about right here. Yeah. Check this out right here. This is the good stuff. So finding trigonometric functions of special angles using side lengths. We have already discussed the trigonometric functions as they relate to the special angles on the unit circle. Now we can use those relationships to evaluate triangles that contain those special angles. We do this because when we evaluate the special angles in trigonometric functions, right, they have relatively friendly values that contain either no or just one square root in the ratio. Therefore, right, these are the angles often used in math and science problems. We will use multiples of 30, 60, and 45. However, remember that when dealing with right triangles, we're limited to angles between 0 and 90 degrees. So suppose we have 30 degrees, 60 degrees, 90-degree triangles, right? which can also be described as pi over 6, pi over 3, pi over 2 triangles. The sides have lengths in the relation s, square root of 3s and 2s. The sides of the 45, 45, 9-degree triangle, which can also be described as pi over 4, pi over 4, pi over 2 triangle, have lengths in the relation s square root of 2, right? S, and these relations are shown here, right? So these are special right triangles. I would like to rewrite these for you just to make it pop a little bit, right? So if I have a special right triangle like so, right? That's 30 degrees, right? So this is 30 degrees over here. This is 60 degrees, right? Opposite the 60 degree is going to be radical 3. Opposite the 30 degree is 1. And then our hypotenuse is 2. This is the special right triangle that we have here, right? Let me rewrite this one. This is our 45, 45 degree angle, right triangle. Our side lengths are 1, 1, and radical 2. There you go, right? These are our special right triangles. I don't remember the unit circle, but I remember this. And from this, I can derive anything. I can answer everything, right? For me, this is the sauce right here. All right. So we can then use the ratios of the side lengths to evaluate trigonometric functions of special angles, right? So how to, right? Given the trigonometric functions of a special angle, evaluate using the side length. So here's how you do it. Step 1, use the side length shown in the figure, right? For the special angle you wish to evaluate. Step 2, use the ratio of the side lengths appropriate to the function you wish to evaluate. Very nice and simple. All right. All right. Feel like we know how to do that already, so time is against us a little bit. So let's move on. So now we want to talk about using equal cofunction of complements. This is new. This is new now, right? So, all right. If we look more closely at the relationship between the sine and cosine of the special angles relative to the unit circle, we will notice a pattern. In a right triangle with angles of pi over 6 and pi over 3, we see that the sine of pi over 3, namely square root 3 over 2, is also the cosine of pi over 6, while the sine of pi over 6, namely 1 over 2, is also the cosine of pi over 3. So sine pi over 3 is equal to cosine pi over 6, which is equal to square root of 3 over s over 2s, which is just square root of 3 over 2. And sine pi over 6 is equal to cosine pi over 3, which is equal to the side divided by 2 side, which is equal to 1 over 2. All right? These are cofunctions. That's what we're talking about right now. Cofunctions and complements. Right? They complement each other. All right. On your homework, they're going to ask you for some of this as well. All right. So here we go. We have a figure up here, figure 9, right? So the results should not be surprising because as we see from figure 9, the opposite side, right? The opposite, the side opposite the angle of pi over 3, right here, right, is also the adjacent side to pi over 6, right? So sine of pi over 3 and cosine of pi over 6 are exactly the same ratio of the same two sides. So square root 3 side and 2 side, right? Similarly, cosine of, excuse me, cosine of pi over 3 and sine of pi over 6 are also the same ratio using the same 2 sides. So side and this 2 sides, right? So the interrelationship between the sines and cosines of pi over 6 and pi over 3 also hold for the two acute angles in any right triangle. Since in every case, the ratio of the same two sides would constitute the sine of one angle and the cosine of the other, since the three angles of a triangle add up to pi, and the right angle is pi over 2, the remaining two angles must add up to pi over 2. You remember all the angles inside of the triangle, they add up to 180. That's where this is coming from. All right. So that means that the right triangle can be formed with any two angles that add up to pi over 2. In other words, any two complementary angles. So we may state a co-function, excuse me, identity. If any two angles are complementary, the sine of one is the cosine of the other and vice versa, right? So the sine of alpha is equal to the cosine of beta, and the sine of beta is equal to the cosine of alpha, right? Cofunction identity of sine and cosine are complementary angles. Here it is, all right? Very, very interesting, very interesting. All right. Let me put that all together for y'all. Check this out. It's going to bring us to a new idea. All right. So using this identity, we can state without calculating, for instance, that the sine of pi over 12 equals the cosine of 5 pi over 12, and that the sine of 5 pi over 12 equals the cosine of pi over 12. We can also state that if for a certain angle t, cosine of t is equal to 5 over 13, then sine of pi over 2 minus t is equal to 5 over 13 as well. Cofunction identities, here they are. I don't remember if this is on your formula sheet or not. So the cofunction identities and radians are listed below. It's not? I don't know. I don't remember if it is, right? But cosine of t is equal to sine of pi over 2 minus t. Sine of t is equal to cosine of pi over 2 minus t. Tangent is equal to cotangent of pi over 2 minus t. Cotangent is equal to tan of pi over 2 minus t. Secant of t is equal to cosecant of pi over 2 minus t. And cosecant of t is equal to secant of pi over 2 minus t. There you go. Those are your cofunction identities. All right. It's not there, right? There's a lot of stuff there, but I don't remember if that was there. Let me give you a little how-to. So given the sine and cosine of an angle, you want to find the sine or cosine of its complement. Here's how you do it. To find the sine of the complementary angle, find the cosine of the original angle. And to find the cosine of the complementary angle, find the sine of the original angle. There you go. Look at an example. So the sine of t, the original function, right, is equal to 5 over 12. So the cosine, right, of pi over 2 minus t should also be equal to should also be equal to what? Say it. 5/12. Perfect. 100. That's easy. Right? That's it. Co-function identities. Right?
There's a lot of it.
Mm, not really. It's different. Different idea. All right. So using trigonometric functions. So in previous examples, we evaluated a sine, cosine, and tangent where we knew all three sides, but the real power of right triangle trigonometry emerges when we look at triangles in which we know an angle but do not know all sides. Oh, this is genius right here. So given a right triangle, the length of one side and the measure of one acute angle, you want to find the remaining sides. Here's how you do it, right? Step one. For each side, select the trigonometric function that has the unknown side as either the numerator or the denominator, your choice. The known side will in turn be the denominator or the numerator. Write an equation setting the function value of the known angle equal to the ratio of the corresponding side. Step three, using the value of the trigonometric function and the known side length, solve for the missing side length. Perfect. Right there. Perfect. Right there. All right. So let's take a look at an example. All right. Oops. 1 second. All right, here we go. So in this question right here, right, we want to find the missing side lengths of the trigonometric ratios right here. All right. This is simple. All right. This is simple. So I'm just going to redraw this triangle right here. So we said that this was 30 degrees, right? This is A, this is C, and our B is 7. And we already know what this other angle is. It's 60 degrees right here. All right? That's not so bad. All right? So all I have to do, I just have to find one other side, right? And then once I find that other side, I can use the Pythagorean theorem to get the rest. All right? So let's say that I wanted to do, somebody give me something. What do y'all think? Any of the 6 trigonometric functions, your choice. Not sure. Also, I want to bring out that remember that we have our special right triangle that we remember 30 degrees, 60 degrees right here. Opposite the 60 degrees, radical 3. Opposite the radical 3. Opposite the 30 is 1, and our hypotenuse is 2. Right? It's not so bad, right? We could kind of use one to find the other. Right? We have our special right triangle, use one to find the other. Right? Like, I'll give you an example. Over here, the hypotenuse is C, over the known side is 7, right? If I said that the other side, the hypotenuse is 2, over the known side 1, cross multiply. Cross multiply, right? So C times 1 is equal to 2 times 7. Let's call that C is equal to 14. There you go. And all you got to do is use a little Pythagorean theorem and you're done, right? So let's get it. I mean, let me change my color real quick. So A squared plus B squared equals C squared, right? And what did we say now, right? I don't know what a squared is, but I know that b squared is 7 squared, which is equal to 14 squared. So this is a squared plus 49 is equal to, all right, I'm tapped out. I don't know what 14 squared is. Let's look at what that is. 14 squared, what is that? 196, 196. I didn't know that, right? So we're gonna subtract 49, subtract 49. So now what do we have? A squared is equal to, let's borrow this, is gonna be an 8. This is gonna be what, 16? Right? So what's that? That's gonna be 7, I think, and then this is 4, right? And then 1, so 147, something like that, right? So now what do we want to do? We want to square root both sides, get rid of that square. So a is equal to square root 147. There we go. And that's it. That's the whole problem right there. Questions on this? Go down this way or the other way? Right there. Okay. All right. But it's not bad, right? All right. That's it for tonight. All right. Yeah. You're welcome. You're welcome. You're welcome. All right, I'm gonna stop the recording. Those of you watching in, have a great night. See y'all tomorrow.
Okay,
All right. Yeah, today.
Home today,
Mhm.
huh?
No, no.